So now that we know the difference between metals and nonmetals, between a 1s and a 3s, between d orbitals and f orbitals, we want to get into what holds atoms together. So this is all about bond. The three kinds of bonds that we're going to worry about are ionic, polar covalent, nonpolar covalent, pretty much the same thing. And then we're going to worry about some other things, like bonds that hold molecules, not within the molecule, but one molecule to another molecule. So let's concentrate on these three. Ionic is when things take electrons or give up electrons. So there are cations and anions. Hopefully you remember that from the last one. You're talking about something that's extremely electronegative, taking an electron, and something that's not very electronegative, giving up an electron. Those are typically a metal and a nonmetal. So y'all need to make sure you pencil that in there. Ionic things are a metal and a nonmetal. Polar covalent things and nonpolar covalent things are where electrons are shared between atoms. The difference is it an equal sharing, as in nonpolar covalent, or is it an unequal sharing? Let me give you an example. My brother Rob is 4 years older than I am. He is bigger than I am, and as a kid, he pretty much got whatever he wanted when we were alone, because he's bigger on me, he could sit on me and thump me in the head, that kind of thing. Even though we had things in our room that we were supposed to share, because we shared a room, do you think that it was equal sharing? Was it a non-polar covalent brotherhood, or was it a polar covalent brotherhood? It's going to be polar because it was very unequal. He got it whenever he wanted. Is it because that's the way I wanted it to be? No, it's because he was more electronegative. He was more lustful after the things. He was more, he wanted the things more often. And since he was bigger than I was, he got them. So how do you know whether it's ionic, polar covalent, or non-polar covalent? Like everything up to 0.4 is non-polar covalent, 0.4 to 1.7 is polar covalent, and then greater than 1.7 is ionic. So make sure you know those numbers. So this is just kind of a big overlooking view. You guys may want to get this in your notes, or at least print it off or something like that. It gives you a spatial, meaning laid out for you, view of what all the different kinds of bonds are. We've talked about ionic, and you can see that right in here. We've talked about the covalent, you can see that there. The other three are pretty, or the other three, sorry. The other one is actually pretty easy. The metallic bonds occur between a metal and another metal. Covalent stuff is between a nonmetal and another nonmetal, carbon and oxygen. Ionic is between a metal and a nonmetal. So that's, like sodium and chlorine. This would be like copper and iron, something like that. So those are the three main kinds of bonds. For each type of bond, we can discuss many things. We can discuss the bond length. How long is that bond between them? And if you remember, we talked about ionic size. We talked about atomic radius, and all those things have to do with bond length. Bond energy has to do with how much energy is present in that bond. How much energy would it take, say, to break that bond apart? So that right there is bond energy. Bond polarity is that function that we've already talked about, is what's the difference between electronegativities? Are you a polar or a non-polar bond? We can also talk about its geometry. In other words, if you make a molecule, let's say you make water, well, what shape is that? Is it straight? Is it bent? Those kinds of things. Some molecules occupy kind of a three-dimensional space, and so we'll talk about those more in future podcasts about weird geometries like tetrahedral and things like that. We can also talk about the intramolecular forces. In other words, what are the forces that hold molecules together? These bonds up here are all the types of bonds that occur intramolecular, meaning within a molecule. Intermolecular forces are ones that occur between two molecules. Y'all need to make sure you look up lattice energy so you have some idea what lattice energy is. That should be a definition that you guys look up. Any covalent molecule, so for anything that shares electrons, we want to be able to write Lewis dot diagrams. Okay, Lewis dot diagrams are not hard, but these are some basic rules. I want you to get these steps in your notes so that we can work on them in class together. Figure out how many electrons there are. This is not total electrons, this is valence electrons. So for example, take out your periodic table. You can pause here if you want to. Take out your periodic table, look up oxygen. How many valence electrons does oxygen have? Well, it's in group 16. So in group 16, if you subtract 10, you get 6. That's how many valence electrons it has. And you do that, you subtract 10 because that's a general rule. If you wanted to, you could write out the electron configuration. 1s2, 2s2, 2p6. And so how many are in the second energy level? You get 2 in the s, 4 in the p. I said 2p6, but that's wrong. It was 2p4. 4 in the p, and that's a total of 6 electrons. So oxygen has 6. Look up chlorine for me. Chlorine, Cl, is in group 17. Subtract 10. That means it has 7 valence electrons. Last one, how about sulfur? Sulfur is in group 16. Again, 6 electrons. Not really the last one. This will be the last one. What about silicon? Silicon, Si. Silicon's in group 14, and so it has 4 valence electrons. So what you need to do in these steps is, for each element, figure out how many valence electrons there are and add them up. So in a molecule of water, H2O, how many electrons are there? Hydrogen has 1, and there are 2 hydrogens, so that's 2 electrons. Oxygen has 6, so that's a total of 8. Then these other steps we'll practice in class, and we'll do this very, very quickly, and you will just become an expert. Sometimes you might have a molecule that is a double bond and a single bond right next to each other. And what we want to realize is that double bonds and single bonds don't just live in one place. If you have a double bond and a single bond, they don't just live in one place. So let me draw you an example. All right, so here's an example. You've got a carbon double bonded to another carbon and single bonded to a third carbon. Does that double bond just stay in one place and that single bond just stay in one place? No, because we know that electrons don't just hang out in one place. They're constantly moving. You've got this idea of a double bond and a single bond. I just want you to know that it kind of resonates. These electrons are constantly moving around. So the double bond could be on the right-hand side and the single bond on the left. You could draw 2 different resonance forms, meaning it doesn't always have to look like this. You could have a single bond on the left-hand side and a double bond on the right. You really, if you want to get down to it, really this is a bond and a half, and this is a bond and a half. Because over time it averages out. This is 2 and this is 1. What's the average bond? Well, it's 1.5. And yeah, if you actually go in and measure the bond length and measure the bond energy, you find a bond energy and bond length not of 2 and 1, but of 1.5 and 1.5. 2 examples of that are something called ozone and carbonate. And when we work the Lewis diagrams, we will actually draw both ozone and carbonate. Just to remind me, ionic stuff has lattice energy. Lattice energy is the energy released when ionic stuff forms. Now you guys have all seen lattice. Lattice is, you may just not know about it, but lattice is that stuff like underneath decks. Lattice energy is when those crystals form. It forms that lattice of positive and negative ions. Lattice energy is the energy released when those things crystallize. The higher the lattice energy, the stronger the bond is, because if it releases that much energy, that's also how much energy it would take to break those bonds, to split up the sodium and the chlorine. Ionic stuff tends to be super, super hard, and you know that because salt is hard, and it's tough to bend. You can't take salt crystals, or granite would be a good example of something that's ionic. You can't take it and bend it because it's locked into those positive and negative ions. And if you get them 2 positives next to each other, if you try to bend 2 positives next to each other, they don't really like that. They hate each other. They repel. You can't really bend ionic stuff. Metallic bonds are 2 or more metals bonded together. If you remember, metals always want to get rid of electrons. They're cations. They want to lose electrons. Those electrons that it holds on its outermost surface, those valence electrons, no one wants them, because if you get a bunch of metals together, it's like a bunch of Girl Scouts getting together trying to sell each other cookies. Everybody's got cookies to sell. No one wants to buy them. Metals are the same way. Everybody's got electrons around them. Nobody wants to take them. So when I say it's a sea of electrons, really it is. It's a pile of loosely held electrons that no one's really looking out for. And because it has this pile of electrons, those electrons act as a lubricant, okay, because they're not tightly held. So these electrons allow the atoms to slip past each other. Therefore, they're malleable, meaning you can beat them into thin sheets, okay? They're flexible. They're ductile, meaning you can push them through a hole and draw it to form a wire. Not draw it with a pencil, but pull it out of that hole and you'll form wire. And that's actually how they make wire, is they take metal and they draw it through a die, which is a metal plate with a small hole in it, and that's how you make wire.